Okay, so now what I wanted to do is I wanted to move into kind of a real world situation here. And the real world situation is the class number 3 agenda here, where we have a situation. The simplest example for me as far as a teaching example is, and I don't know if you guys, do you deal with people who have pain perception or in pain? Mm-hmm. Okay, so pain is a good thing to deal with. The simplest thing that I can help or that I teach with in this example is morphine. You have people taking morphine sometimes for pain. Yeah, kind of, it's a happening thing. So this is just a statistical example. We're not making any political, ethical, or any other statements here, just used for this sake. There's going to be another example of that as well. So read the question there. I'm testing to see if a high dose of morphine helps pain perception, 1 to 15 scale, higher number indicating more pain. I give 3 people a high dose of morphine, 3, 4, and 5 are their scores. Second group gets a low dose, 4, 5, and 6. Third group gets saline. Sorry about that. Compare the, it shouldn't have had that last little sentence there. Compare the high dose to the low dose in a control group given nothing. So just, you can cross that last line out there. It was just a typo there. I wasn't supposed to have that sentence. So let's go to the questions there. Does it look like the medicine worked? What do you guys think? Does it look like the morphine worked here? Why would you say yes?
Because within each group, when they had a lot of the medicine, their pain was much lower. Below the medicine is somewhat lower than when they didn't have any medicine.
Than when they didn't. What measure of central tendency do people usually use to kind of describe this?
Like averages?
Say again?
Central tendency, so averages?
Yeah, the mean. You would take the mean of each group, and if you take the mean of the group that had the high amount of morphine, you'd get a mean of what?
4.
4 there. If you took the group that had the low dose of morphine, 5 there. Does it look like there's much of a difference between those groups? No, probably not, but the group that got nothing,
Got a 12.
yeah, the mean there was a 12, so there's a lot of pain there. So it looks like the morphine was somewhat effective here. Now the question would be, could we do a t-test on this?
We could do a bunch of t-tests.
We don't know what their starting pain is.
That's a true statement for a different occasion. We'll get to that equation. That would be a 2-factor equation that we'll get to later, a 2-factor ANOVA situation. You're exactly correct with that what you would want to do technically is you would want to measure their pain beforehand, then give them the morphine and measure their pain after. Then you would kind of have 3 different levels here and groups, and before and after. That would actually be the right way to do this, but the simple teaching approach on the next level of 1 factor is here. So you're you're good. I was trying to validate. So the idea is it looks like the medicine worked. Yeah, you could do a t-test. But the problem is, how many t-tests would you actually have to do here?
Maybe 3 times 3.
Yeah, you'd have to do 3, and if you actually had 4 or 5 levels of morphine, you'd end up having to do a lot of t-tests, and is that a good idea? The point right now is no. If you do a lot of t-tests, you run into what's called a chance of making a type 1 error, of saying something significant when it's not. So we'll get back to that point a little bit later, but you wouldn't want to do a bunch of t-tests. If you have more than 2 levels, you do an ANOVA, one-way ANOVA. So in this situation, we would do an ANOVA. What's the independent variable? The variable being manipulated is what? Medication. Or medication dose. Are you all right?
Nope.
It's killing you. Do you need some morphine?
No.
Sorry, I don't have any. It was just a statistical example.
Thank you.
Hang in there, though. So the idea is you would have 1 independent variable, kind of the condition, if you would, and how many levels for that independent variable? 3 levels. None, low, and high. What's your dependent variable?
Pain. Level.
Pain perception. Mm-hmm. So in this situation, 1 independent variable with 3 levels and 1 kind of continuous dependent variable, that's an ANOVA. That's a one-way ANOVA. because we're going to get you. If I may quote a song. Okay, I'll stop. So we have an ANOVA here, we have the IVs and the DVs. So the computations on this situation. The computations you have to get, if you looked at the picture from before, you have to get the variance between the groups, and you have to get the variance within the groups. So let's actually start, how do we want the variance within the groups to actually be?
Less?
We want that number to be pretty small, actually. So 4, 5, and 6. Or actually, let's start with the first group, 3, 4, and 5. You guys remember how to compute a variance? The sums of squares over the degrees of freedom. Sums of squares over degrees of freedom is variance. So if you want to write that down, sums of squares over degrees of freedom. Does anybody know the sums of squares for the numbers 3, 4, and 5? 3 minus 4 squared plus 4 minus 4 squared plus 5 minus 4 squared. You take the score minus the mean and square it. We did that, I think, at one point in time. 3 consecutive numbers, the sums of squares is always 2. So if you have 3 consecutive numbers, the sums of squares is always 2. You can just kind of know that. So 3, 4, and 5 would be 3 minus 4 squared plus 4 minus 4 squared plus 5 minus 4 squared. And that would equal 2. So 3, 4, and 5, what are the sums of squares there?
2.
2. 4, 5, and 6, what are the sums of squares there?
2.
2. And 11, 12, 13?
2.
2 again. So the sums of squares within groups equals what?
So you add it all together, then that's...
You add it all up, you do the hokey pokey. Oh wait, I'm not at Virginia Tech, sorry. And what does the sums of squares within group equal?
6.
6. Look at the table down below. Sums of squares within groups equals?
6.
6. And then to get the variance, you need the sums of squares over degrees of freedom. How many people do you have in the first group?
3.
3. So how many degrees of freedom within that group?
2.
2. Second group?
2.
2. Third group?
29.
29. I like that. So what are the degrees of freedom within group?
6.
6. So if the sums of squares within group is 6, the degrees of freedom within group is 6. Mean square is another term for variance. The variance within group is
1.
1. 6 over 6. Sums of squares over degrees of freedom. Don't worry if you don't know these details. They're really not critical, but it's kind of reviewing things a bit. So is that good news or bad news for us? Do we like this?
No.
Why don't we like this?
I don't like variance with 1.
Well, what is this variance looking at? Variance within group, numerator or denominator? And the denominator is measuring
Error.
error.
That's actually not bad.
It's actually probably going to be good. We want that number to be low.
Yeah.
That's the whole idea. You want the variance within group to be low. Sums of squares between groups. How do we want that number to be?
High.
We want that number to be high. I'm going to just verbally share with you a little bit on how you compute that because we don't want to go into that much detail here. That number, you basically get, what is the grand mean for this whole thing? You got what, 12, 4, and 5. What does that add up to be?
21?
21.
21. So what's the grand mean? 12, 4, and 5. 21 divided by 3. It's 7. And so the idea is to get the grand mean, you take each group mean, subtract it from the grand mean, square it, and multiply it by the number in the group. So we want the sums of squares between groups to be what? High or low?
High.
High. Does 114 look good?
Yep.
Yes, it does. That's all we need to say about that. So 114 looks good. Degrees of freedom 2, where does that come from?
Just feeling, nope.
How many groups do we have?
3.
So how do we get to 2?
-1.
There you go. Number of groups minus 1. So the degrees of freedom between groups is 2. How did it come up with 57?
114 divided by 2?
There you go. 114 divided by 2 is 57. So the variance between groups is 57. The variance within groups is 1. So what's the F score?
57.
57. Good news or bad news?
Good news.
Good news. The SIG says 0, 0, 0. How would you write that out in APA style? Does anybody know? You'd write F, if you want to write it in your notes, 2, 6 in parentheses. 2, 6, degrees of freedom numerator 2, denominator 6, equals what? What is the obtained F value here? 57, and then you'd write P, would you write 0, 0, 0? Does anybody know how you would write that out?
No, because you don't like P equals 0.
You never write P equals 0, 0, 0. Do a lot of people in OT, PT, and PA write 0, 0, 0? That's not quite right. You write P what?
Less than.
Less than 001. So is this good news or bad news for us?
Good.
This is good news. This means we have a statistically significant result. We do have statistical significance here.
Is there a statistical significant threshold for F values?
In this situation, in most situations, the computer, instead of a textbook, will simply tell you the probability of getting a 57 due to chance. And that's the 0.05 situation. If the value comes out to be less than 0.5, you say you did it, you're significant. If the F value or if the SIG value is greater than 0.5, then you're not significant. And of course, we have that marginal zone as well. So the computer is basically going to tell you what you need to know. I've worked with a few folks up here, and sometimes the Fs are less than 1, and then you know you're not significant. The Fs can be 1 or 2 and still be non-significant, and so you figure that out. So we have a significant result here, but we still have a problem, kind of the final problem here. It appears the drug had a positive effect on things, but what don't we know? What don't we know here? So is the high dose
We don't really know.
great? Is it better than the low dose? Is it better than the no dose?
Yeah, so we still don't know the differences between the 3 different groups.
Yeah, you don't know the differences between the three groups. Now, what would we almost want to do here that was brought up at the beginning of this discussion?
More dependent variables.
Well, not more dependent variables, but what kind of statistic did we talk about? You'd want to actually kind of compare the groups a little bit.
Right.
And what do we usually do to compare two groups?
That's t-test.
We usually do a t-test, but there's a problem with that. What did we say that problem was?
3 levels.
Well, we said the problem was you run into kind of that type 1 error situation. So what we do instead are called post hoc tests. Post hoc tests are kind of like t-tests, but they're just much more conservative. They're just much more conservative. And since it is November 7th, there are about 15 different post hoc tests that one can do. But since it is November, one of my personal favorites right around Thanksgiving is the Tukey test. There are like 20 different ones, SPSS, but actually I usually use the Tukey test.
Well, that was my question, because I've been in SPSS before, and you look at all those, and it's like, Okay.
Different
You know, and then
strokes
you
for
start-
different
you
folks.
Start reading all the which one is which, and I would get buried.
All
trying to figure out which
researchers,
one is-
all researchers have different preferences for things. Some are more conservative than others.
Okay.
The t-test, or the Tukey test, a lot of people use. I was even looking at SPSS, there's a Tukey's B test. Tukey was a famous statistician, actually. But there are all sorts of them. Some are more conservative than others, because the idea is you want to avoid that problem with, let's say you had 5 levels of an IV. The problem that you would avoid by not doing all these t-tests, it's called a family-wise type 1 error. It's a family-wise alpha error. You want to avoid that. So if you have a significant ANOVA result with 3 or more levels, you do a post hoc test. Some people do the Bonferroni, some people do the Chaffee. I usually do a Tukey's test.
So it depends on how conservative you want to be. That's the gist of it.
Kind of, and it almost, I would even go less than that. Different people just kind of have different preferences for things.
Okay.
It's really kind of,
So if you do one of those in an article in your report, you did the Tukey, they're not going to slash you because
yeah, nobody's going to say, why didn't you do the Bonferroni? And if they do, guess what you do?
You just run the other one.
You run the Bonferroni or the Chaffee, and you say, why is this person bothering me so much?
Okay, well, that's good to know.
I've had similar situations arise on articles I've submitted teaching statistics and people making statements about why did you do this and that, and just tried to answer in a diplomatic way that we chose this test for this reason, and that seemed to be the proper logic. But if you really want me to do this other one, I'll be happy to do it for you. And then they usually are like, oh, okay, that was your rationale. That makes perfect sense to me. I'll shut up now. So we do a Tukey's test to really avoid kind of, it's like a t-test. And if you look at the example here with the Tukey's test, how does it look here? So we got that column, mean differences. That's kind of the important column. What's the first mean difference it gives you?
So,
Gives you what number there for mean difference number 1 there? 7. Where does that come from?
so that's.
That was the average thing.
That was the average thing. It kind of compared. I like that. That was the average thing.
Divided by 3 one time today.
Yeah, that was the no drug, 12, minus the low dose, which was 5. 12 minus 5 is 7. Doing the Tukey's test, was that difference significant?
Yes.
Yes, so you would say if you were writing up a manuscript, a post hoc test showed, Tukey's post hoc test showed that the low dose was better than no drug. How about the high dose?
Yes.
Yes, that also worked better than the no drug. What about the low dose versus the high dose here?
Not much different.
Only 1 point. That was the 4 versus the 5. So you would say there was no difference between the low and high dose. Could this be of clinical importance to you?
Yeah.
Yes,
How so?
because if they're equally,
If they're equally as useful,
You give lower dose.
you always give the
don't wanna
lowest
give more
possible dose
than
that
you-
works.
Yeah.
So this is how we do a 1-factor ANOVA. We put the numbers in a computer program. I'm not going to do that here, but it can be done. Usually 2 columns. 1 column has the IV in it with 0s, 1s, and 2s. The second column has the scores in it with the DV. You run it. It does an ANOVA, and then you say post hoc. It gives you about 20 different choices, 5 of which I've heard of. Now, I'm not a statistician. I'm a behavioral guy that knows a lot about stats. Most statisticians would know all the ins and outs of all the differences there. But Tukey, Chaffee, Bonferroni, those are, I think, the more popular ones that people sometimes use. But whatever you use is probably fine. And in this case, you would write out the F of 2 and 6 equals 57. P less than 0.001, and then you would say a Tukey's post hoc test was done and indicated that the low and the high dose were much better than nothing, but there was no difference between the low and high dose. And clinically, you'd say the low dose is probably fine. Does that work for people? Comments or questions? Okay.
That's the biggest thing for me. I mean, I remember taking stats in my PhD program, and the guy who taught it he was a funny guy. But anyway, he would talk about, which was the part that I liked. He said, you don't have to understand all the math anymore. You just got to put the right equation in the computer. He said, what you got to be able to do is tell the story about the data that comes out the other side.
Yeah.
and that was good. That the hardest thing for me has always been figuring out what's the right thing to put in the computer. Because I'm one of these people that's not math oriented, so I don't need to know how the math ends up there.
Right.
I just need to know that I put the right thing in the computer, and that's the hardest decision to make.
So the right thing into the computer, if you want to write it here, the way you would actually put this data in is you would create, this is a between subject design. The way you would create this is 2 columns. One column would have the 12 scores, the DV. The other column would have the IV. You'd have 1s, 2s, and 3s, and then you'd run the one-way ANOVA on it. And if you're ever at that level of doing things, that's a 5-10 minute conversation with me, and I can instruct you on that. There's no big deal there. But yeah, learning how to understand the output screen is the way. Okay, let's